Welcome back to geometry. Before we jump into 6.5 trapezoids and kites, let's go ahead and solve. This is a problem from the previous lesson that involved a rhombus. And again, it's just good practice to review certain shapes. And even though we're going to be learning about trapezoids and kites today, let's start off with a rhombus. So we're given, one thing that we know about a rhombus is that their diagonals are perpendicular. So we know there's a window of 90-degree angles all the way around. So that helps us out. So we know that angle 5 is going to be 90 degrees. Next, we can move 90 here and here. We know all of these sides are congruent because all sides of a rhombus are equal to each other. Alright, what else do we know? We were told that measure of angle 1 is 40 degrees. Okay, so there's also a theorem that says the diagonals of a rhombus will bisect the opposite angles. So what that means is, since angle 1 is 40 and it's cut by this diagonal, that means angle 2 is also going to be 40 degrees. And that also means that if we have 40 and 90 or 130, that means angle 3 has to be 50 degrees. And we're back to this same theorem that in a rhombus, their diagonals will bisect the opposite angle. So since angle 3 is 50, angle 4 has to be 50 degrees as well. On problem B, they want, even though measure of angle 5 is 90 degrees, they still want us to solve for m. So we're going to take 3m minus 9, set it equal to 90. 3m equals 99, m equals 33. If measure of angle 1 is 40, or also let's just do it like this. Since angle 1 and angle 2 are the same, let's set each of these equal to each other. 2a plus 1 equals 5a minus 8. That would give me 3a is equal to 9, which means a is equal to 3. And measure of angle 1 and measure of angle 3, well, there's a few ways that we can do this. Alright, let's take 7a minus 3. We're going to take 2a plus 12, and we're going to add up 90. And those are the three angles that are in this triangle. So it has to equal 180. So 9a plus 9 plus 99 equals 180. 9a equals 180 minus 99. That's got to be 81, right? And then a is equal to 9. Looking at the algebra review, we have x squared plus 6x. These share an x. So I'm going to pull an x out and I get x plus 6. And that's still equal to 0. Now I have to set each of these values equal to 0. So I take my x and I set it equal to 0. I take my x plus 6, I set that equal to 0 as well. So my first answer is x is equal to 0. My second answer, when I subtract 6 on each side, I get negative 6. This time I get x plus 5 times x minus 2 is equal to 0. X equals negative 5. X equals positive 2. This problem I get x plus 6 squared is equal to 0. And really that's just saying x plus 6 times x plus 6 is equal to 0. Solve for x. X equals negative 6. Alright, to the new shapes. We are being asked, are all trapezoids parallelograms? No, we have a new species today. Okay, we're no longer dealing with mammals. Maybe we're dealing with some kind of reptile. I don't know. But are all trapezoids quadrilaterals? Yes. Okay, they are because they have 4 sides, 4 angles. So this would be a yes. Alright, to our mid-segment. You may recall that in the past we had a mid-segment involving a triangle. That was in our last unit. And this is similar, but it's not exactly the same. This is a mid-segment for a trapezoid. And what we're going to say is that this is a segment joining the midpoints of the two non-parallel sides. So if we think about that definition, let's look at our shape. We have a trapezoid down below, and what we should be shown here is that these two segments are the same and that these two segments are the same as well. Okay, and the fact that all three of these lines are parallel, that makes X has to be a mid-segment. Okay, it's going to cut the opposite sides in half, and then it's always going to be parallel to your two bases. So we have our base 1 and base 2, or you could call this base 1 and this base 2. So to find our mid-segment, we take base 1 plus base 2 and we divide it by 2. So in a sense, the mid-segment is an average, let's spell that right, is an average of the two bases in a trapezoid. So we're going to say that our mid-segment is equal to B1 plus B2 over 2. In this problem, our mid-segment is unknown, it's X. Our base 1 is 21. Our base 2 is 7. We divide that by 2, X equals 14. In this problem, we're given 10 as our mid-segment, so we actually have to work backwards. Our base 1 is going to be 2x minus 4. I'll put this value in parentheses. And then plus base 2 is going to be x minus 3. And then we have to take the average or divide by 2. Alright, from there, I would times both sides by 2. The reason why I do that is to eliminate this fraction. And so now we get 20 is equal to 2x plus x is 3x. Negative 4 plus negative 3 is negative 7. 27 is equal to 3x, which means x is equal to 9. If I plug in 9, I get 18. 18 minus 4 is 14. 9 minus 3 is 6. Now, one thing that I didn't show over here is that when x was 14, do you see how it is an average or halfway between 21 and 7? That'll always be true for mid-segments of a trapezoid. This length will always be halfway between 7 and 21. Same thing over here. We have 14 and 6. What number is halfway between 14 and 6? That would be 10. And again, I can show that these two lengths are the same and these two lengths are the same. Alright, next problem. They want us to label the isosceles trapezoid form. Now, how do we know this shape is isosceles? Well, they show us two marks here. Okay, so we have these two marks, and these two sides are parallel, so therefore it's an isosceles trapezoid. Let's label our points farm. So we have F, we have A, we have R, and we have M. Okay, and then they're telling us to draw a segment from A to S, so that FASM is a parallelogram. So we want to draw this line so that it's parallel to FM. We'll do the best we can. And then this new point is going to be called S. And then let's put arrows here to show that these lines are parallel. Also, since we just created a parallelogram, we know that these two sides are the same. Alright, if FASM is a parallelogram, then what I just said is that the opposite sides are each congruent, so FM is congruent equal to AS. Furthermore, I can say if AS is congruent equal to AR in the shape on the right, then triangle ASR is now an isosceles triangle. Alright, since we have an isosceles triangle, let's put an angle 3 here. Therefore, I can say that angle 3 is congruent equal to angle 2. Why is that? Because these two sides are the same, which makes these two angles are the same. Alright, furthermore, if I look at these two lines which are parallel, and I look at angle 1 and angle 3, if I were to extend these lines all the way out, you would see that angle 1 and angle 3 are corresponding angles. So angle 1 is congruent to angle 3 and angle 2. because angle 1 comma angle 3 are considered corresponding angles. Alright, next we're going to draw in two diagonals, and it's going to set up our first theorem. And actually, before I do that, I have just now proven by doing this, if we look at angle 1 and angle 2, we can now see that the base angles of an isosceles trapezoid are each congruent. Okay, and I just proved that with angle 1 and angle 2. So that's one theorem that we have. It's called the base angles of an isosceles trapezoid are each the same. They're each congruent. Alright, next we're going to draw in two diagonals. Yeah, let's go red. So here comes one diagonal. Here comes our second diagonal. Alright, and by doing that, we have now created two overlapping triangles. So we're going to redraw that first triangle. And so there's F, there's M, and there's R. Alright, and then let's redraw the second triangle, which is going to look something like this. And so here's A, here's R, and here's M. And next, let's mark it up the way it was marked up in our shape. So you look at FM, it has one mark. You look at angle 1 is here, and we have this. And then you look at AR, and we have this mark, and then angle 2, and it has this mark. So as it sits, these two triangles are almost congruent. We have side angle, side angle. Well, since these triangles overlap, we can say that MR, Mr., is congruent equal to RM by the reflexive property. They're shared. So we can put two marks here and two marks here. So what I can now say is that these two triangles are each congruent. So let's call this triangle FMR is congruent equal to triangle arm. And why is that? Well, by side angle side. Alright, well next they're asking us a very important question. It says, what can you now say about the diagonals of an isosceles triangle? Well, by CPCTC, since these two triangles are each congruent, I can put 3 marks on FR and 3 marks on AM. And when I look at this shape, I notice that FR was my first diagonal and AM was my second diagonal. So what we are now allowed to say is that the diagonals of an isosceles trapezoid are each the same. They're each congruent. Okay, from the last page, this was our new theorem and we had this written down at the very bottom, but it just says that the diagonals of an isosceles trapezoid are each congruent. So that was from the last example that we did on the previous page. So let's take a look at this first problem, and it's pretty simple. It's saying find the missing angles of the isosceles trapezoid. So one thing to note, we know that in isosceles trapezoid that the base angles, plural, are each congruent. So the base angles are congruent. So we can think of, even though x and y are on top, x and y is, or segment xy is still considered a base, because we have two bases. You know, it's base 1 and base 2. So if we were to flip this around, you would have x and y on the bottom, and that would probably be easier, or it would be much easier to see that these two angles are the same. So 156 for angle x, we can put 156 for angle y. These two angles are each congruent. Well, if we have 360 degrees total in a trapezoid, and we just used up 312 degrees with 156 and 156, that means we have 48 degrees left. Alright, And since we have 48 degrees left, we have two base angles left. These two angles are each congruent as well. That means these angles have to be 24 degrees. One other thing to note here is that keep in mind these two lines are parallel. So when we extend this line out, and we extend this out, and we extend this out, these are same side interior angles, and they add up to 180 degrees. And so that would be true as well. We're going to skip the problem that involves the spider web, but we are going to look at the kite next. So for the kite, let's write down what we have. We have a quadrilateral with two pairs of adjacent sides that are each congruent. Okay, so how I show that is these sides are considered adjacent sides. They're side by side, and these sides are considered adjacent sides. Okay, so that's what I know from the definition of a kite. These two sides will always be the same. These two sides will always be the same length. They want us to label this kite salt, so we're going to put S at the bottom, A, L, and T. Alright, next, go ahead and draw in one diagonal from A to T. We'll try and do this as straight as we can. There we go. Alright, now, by doing that, we have actually created 6 triangles. And let's enter this point where they meet. It'll be salty, so we'll put point Y is where these two diagonals meet. And so we have one triangle here and two triangles, 3 and 4, but then we also have this big triangle, triangle lat. Okay, and actually they want us to call it triangle TLA. So let's redraw triangle TLA, and they are overlapping triangles again. That wasn't so hot. Alright, so there's T, there's A, and there's L. And then we also have TSA. And so again, this is a horribly drawn triangle, but there's S and there's T. So from this marking, we see that LA is congruent equal to AS. We see that LT is congruent equal to TS. And since they both have AT is being shared, correct? So these two sides are equal to each other. So what I can say is that these triangles are each congruent. They are congruent triangles by side, side, side. Okay, now that they are the same triangle, we need to then mark for congruence, and we can do that using CPCTC. So angle A is congruent equal to angle A. So these two angles are the same. Next, I have angle L and angle S. I'll put 2 marks, angle L and angle S. And that's the entire angle, right? Angle L and angle S. And then I see that we have angle T and angle T. So these two angles are the same as well. Alright, we're just getting started. We're going to do this again. Next, we're going to take our smaller triangles, and let's call this triangle lay and triangle say. So where can I draw this? Let's go up here. Here's triangle lay, L, A, and then Y. And then below it, we have this triangle, which is going to be called say. And again, we have A and Y here. Alright, again, let's mark what we know. We have a mark between LA and AS. We have a mark at angle A and angle A. And then just like last problem, since these are overlapping triangles, AY should have 2 marks and AY. So we see once again that these two triangles are each congruent. Now what we can do next is we can put 3 marks on LY and 3 marks on YS by CPCTC. So let's show that as well. Now I can put 3 marks on LY and 3 marks on YS. Alright, the other thing that I can assume is that these lines are straight, And so this forms a linear pair, okay? And let's just label this angle 1 and angle 2. Well, if I look at angle 1 and angle 2, since this forms a linear pair, and this is angle y, and angle y is congruent and equal to angle y by CP/CTC, right? Well, since they add up to 180 degrees and they're the same angle, if I call this angle x and angle x, x plus x would equal 180 degrees because of our linear pair. That means angle 1 and angle 2, 2x would be equal to 180, x equals 90. So what I can now do is I can put a 90-degree box all the way around. All right, so let's fill in the blanks. We have if triangle, and I guess they want us to call this triangle tall. Actually, let's just use TLA again. So we're back to the first two triangles. If triangle TLA is congruent and equal, and if I go TLA, I would have to go triangle TSA. Then AS is congruent and equal to AL, which we've already shown. All right, the other thing that's important, please underline this as well, that segment AT is the perpendicular bisector of LS, okay? And that should make sense because we created 90-degree angles. We also show that these two lengths are the same, so this point is a midpoint of segment LS. So AT is actually the perpendicular bisector of segment LS. The other rule that we can draw from kites is that the diagonals of a kite are perpendicular.